Hello, welcome to lecture 3 of second module of the course. In this lecture, we will continue our discussion on transmission line and we will see how we can quantize a discrete transmission line. So let us begin. In the last class, we completed our discussion on Cooper pair box. There we saw that if we are to couple a Cooper pair box device to radiation, the radiation must be a microwave, and in order to enhance interaction between a Cooper pair box or two-level system, the kind of two-level system that we encounter in circuit quantum electrodynamics, it is better to put the qubit or the two-level system inside a cavity because it will ensure long interaction time between the Cooper pair box and the radiation and high intensity of the radiation inside the cavity. And we can have a microwave cavity using the so-called transmission line, and we discussed about transmission line. It can be constructed by considering, say, two metallic wires parallel to each other, or a coaxial cable, two concentric cylinders, metallic cylinders, that is also a transmission line. The advantage of this coaxial cable is that there would be hardly any stray field at all outside, and that is advantageous, and the speed of the signal in both the cases is going to be constant. That is, it is not dependent on either wavelength or the frequency. And we also learned that how this coaxial cable model, which is a three-dimensional one, can be utilized to design a two-dimensional version of the transmission line on a chip. This we discussed. And finally, we discussed how this transmission line can be represented in circuit. Using a circuit, for that we use this two parallel wire model. The idea was that we divided these parallel wires into a number of unit cell size of length A, and each cell comprising of a capacitance and an inductance, and this capacitance and inductance are linear in the cell size, and ultimately our goal would be to make this cell size smaller and smaller, tends to 0, so that it gives us a finer grid. And our goal today would be to discuss wave propagation in the transmission line, and basically to get a wave equation and convince you that okay, indeed this model or this kind of setup supports transmission of signal. And then we are going to quantize the transmission line. Finally, if time permits, then we'll start discussing transmission line resonators. So before we go further, let me first remind you about the so-called LC circuit, which is the most elementary unit cell of transmission line. So let us remind ourselves. So we have an inductance and we have this capacitance here. Okay. And first of all, let me introduce the sign convention for the charge. Let us say the upper plate of this capacitor has positive charge and the lower plate has negative charge. Say the charge Q. Okay. Here it is represented by this capital Q, and say the current I flows in the direction as I showing here. Then as you can see that the charge has to decrease with time, so Q dot should be, I can write it as minus I, because charge is decreasing as the current is flowing. And on the other hand, if we look at the voltage drop across the inductance, then it would be given by, suppose this is the inductance and the voltage is applied along this direction from this positive to negative, then this voltage drop across this inductance L would be L di dt, because it will take a bit of time for the current to flow through it when you apply the voltage. So this is the well-known expression, all of you know. On the other hand, the voltage across the capacitor is given by charge divided by the capacitance C, and is obviously equal to L di dt. Okay, and or I can just write it as L I dot, which I can further write because Q dot is equal to I minus I here. Okay, using this I can write it as minus L Q double dot. So I get an differential equation for the charge, that is Q by C is equal to minus L Q double dot, or I just write Q double dot plus 1 by LCQ is equal to 0. As you can easily see that this is a second order differential equation for charge. It is the equation of motion for charge in an LC circuit, and which we can write as Q double dot plus omega square Q is equal to 0, where obviously omega square is equal to 1 by LC. So this is a well-known equation, all of we know. This equation tells us that charge Q oscillates simple harmonically in an LC circuit. Now let us go back to our transmission line. Say there is a charge at every node and there is current flowing between the nodes. Say charge Q denoted as Qn in the nth node, and then in n plus 1th node the charge is denoted as Qn plus 1, and here we in the n minus 1th node charge is denoted as Qn minus 1, and so on. And first actually we will consider the discretized version, and then we will go over to the continuum version by assuming that the charges vary very slowly as a function of position. Let the current flowing between the node n be denoted by In. That means a current that is flowing towards the node n, let me denote it by In, and then current flowing towards node n minus 1 be denoted as In minus 1, and current that is flowing towards the node n plus 1, let me denote it by In plus 1, and so on. Now you see the charge building up at a node is determined by current flowing into it and out of it. So we can invoke the so-called charge conservation at a particular node. If I invoke that in the for this nth node here, then I can write this charge conservation as this. Say rate of change of charge at the nth node is equal to, that is the current flowing towards this nth node and the current flowing out of it. So this is one equation we obtain, that is this equation, let me denote it as equation number 1. This equation is basically referring to the charge conservation principle. On the other hand, this current In is driven by the voltage drop between this node n and n minus 1, and this voltage drop would be here in this n minus 1th node. The voltage drop would be Qn minus 1 divided by C. On the other hand, here at the nth node it would be Qn divided by C. So this is the voltage drop, difference in the voltage, and that has to be equal to the current through this the voltage through this inductor L here, and that would be L din dt. So we get another equation for using this voltage drop thing. Okay, the current, let me reiterate again that this current IN is driven due to the voltage drop at node n-1 and n. Okay, so now let us see how these two equations look or appear in the continuum domain. To do that, let us say, let me draw the transmission line once again here, this discretized version. Let me say I have like this. This is the okay, let me first draw it, then I will explain. So I have this nth node, that is Qn here, and this is Qn minus 1. Current is flowing towards the nth node here, and here it is Qn plus 1. So this is In plus 1 and so on. This is In minus 1, and this is inductance is L, capacitance is C. Okay, let us say in the continuum limit, as we have learned earlier, that we can actually divide this transmission line into a number of cells, say along this x direction. If I just break up this transmission line into several small number of cells, each cell of size say A, so this is along the x direction I am taking. Now as A tends to 0, I can assume that as the cell size is getting smaller and smaller, let us say I have a current flowing through this transmission line that is smooth like this. Okay, and this is a function of position. Now if I am interested in knowing the current at the nth node, let us say at this particular point, if I, let us say I have, okay, something like this. Oops, okay. Alright, something like this particular point in the nth node, I have to evaluate the current, and this will basically refer to x is equal to n into A, and then current at the nth node is simply current that is measured at the point x is equal to Na. So we can write actually the difference between the current in the node n plus 1, the difference between the current at n plus 1 and In at nth node, that would be nothing but the, I can write it as, it would be nearly equal to the slope of the current at the position x is equal to Na. So I think you are getting the idea here. I am just invoking or taking this, when I am writing this expression, I am using my knowledge of differential calculus. So actually using this prescription, I can write my equation number 1 as well as equation number 2 in the continuum limit. That means when A tends to 0, as follows. Let us say I have this charge conservation equation, Qn dot In minus In plus 1. So this would be in the continuum limit, this would be Q dot is equal to minus A del I del X. Okay, and I have actually used this expression while writing it. So this is what I have in the continuum domain. And similarly the voltage drop equation, which was Qn plus 1 minus Qn, I think, or I can just, this was Qn minus 1 minus Qn by C is equal to L di and dt. This again I can write in the continuum limit as minus A by C del Q del X is equal to L del I del T. Okay, I think you are getting the idea here. So these are the equations that I am writing in the continuum limit. Now let us write down the wave equation in the continuum limit. We can easily get it from this discrete version of the equations. For that I simply need to consider, say, let me say this equation number 2 here. if I consider that equation, say qn minus 1 by c minus qn by c is equal to L di and dt. Let me take time derivative of this equation on both sides. Then what I am going to get is this 1 by c. I have qn minus 1 q, this one, and then qn dot, that is equal to L d2i and dt2. I can get rid of the charges by using this equation that I have written earlier, that is charge conservation, that is 1 by c q dot n minus 1. So that is I n minus 1 minus I n. Okay, I hope you can see that. This is I have for this part, and for the other part we can write I n minus I n plus 1, and the whole thing is equal to L d2 I n dt2. This we can further write it as 1 by c I n plus 1 plus I n minus 1 minus twice I n is equal to L d2 I n dt2. Now you can recognize that in the continuum limit, this part is actually second order derivative of current with respect to position. So in the continuum limit, we can write it as this whole thing as a square by c del 2i del x2, that is equal to L del 2i del t2, or I can write it as del 2i del x2 is equal to LC by a square del 2i del t2. This further I can simplify by writing is at del 2i, which is a function of position and time. Now del x2 is equal to small l and small c del 2i delta t2, which is I is a function of position and time. And here this small l is inductance per unit length, and small c is the capacitance per unit length, and these quantities are actually the physical quantity of the transmission line, and they do not depend on our discretization, independent of that. And okay, now you can see that this equation is nothing but the wave equation. Just recall that the wave equation that you must have learned earlier somewhere is given by, is of this form, that is second order in space and second order in time, where f is a disturbance which is a function of position and time, and this disturbance, this equation simply tells that f propagates or propagates with speed v. Okay, so comparing this equation with our equation that I obtained for current, it simply says that current propagates like a wave in a transmission line with speed 1 divided by square root of LC. So this is the speed of a current signal in a transmission line, and I think and because that this both small l and small c are constant, so this speed is basically a constant quantity. It do not depend on frequency or wavelength. So in the transmission line, if we can create a disturbance of charges like this, and as I explained earlier, so in this whole system we will be able to get a propagation of a signal in the form of current. Okay, and now because we have gotten classically we have got that the current propagates like a wave in a transmission line. That means the current can carry information. So the next problem is to how to quantize this transmission line, how to quantize this particular problem, and this is what we are going to do now. But before actually we do that, let us see how we can quantize LC circuit or LC oscillator, which is the basic building block of a transmission line. So the topic that we are now going to discuss is quantization of LC circuit, and this is going to prepare you for the bigger thing, that is the quantization of transmission line, which we are going to discuss next. In the previous module, we learned the general procedure for the canonical quantization of a classical system. The procedures were as follows. First get the Lagrangian of the classical system, then get the canonical conjugate momentum, get the conjugate momentum, and once you get the conjugate momentum, then work out the Hamiltonian or find the Hamiltonian of the classical system, and then look for the canonically conjugate variables. The canonically conjugate variables are the ones that satisfy the Hamilton's canonical equation of motion, and finally replace the Poisson brackets by commutation bracket and write the conjugate variables as well as the Hamiltonian in the operator form. Now here exactly the same procedure we can apply for quantization of our LC circuit. So we have this inductor with inductance L and this capacitor with capacitance C. We assume that the upper plate is positively charged and the lower plate is negatively charged. Upper plate has a charge say Q and the current is flowing in this direction, and just we have discussed already that Q dot is equal to minus I, and also we have worked out the equation of motion of the LC circuit. Q double dot is equal to minus 1 by LCQ. Now because we know this equation of motion, so we can straightforwardly guess the Lagrangian of the system, that is L is equal to half Li square. You see I'm using different L here. This is for the Lagrangian and this L represents the inductance, minus Q square by 2C. Q here is the generalized coordinate, so I have half L Q dot square minus Q square by 2C. To check if this is indeed the correct Lagrangian, we can actually we must obtain the equation of motion from the Lagrange equation of motion. The Lagrange equation of motion with Q as our generalized coordinate is this, del L del Q here minus d of dt del L del Q dot is equal to 0. Now if you put this Lagrangian expression here in this equation, then you will see the first term is going to give you simply Q by C minus, then the second term is going to give you L Q double dot is equal to 0. So quite clearly you will get Q dot double dot is equal to 1 by LC into Q, and this is indeed the equation of motion. So the Lagrangian that we have written is absolutely correct. Now as regards the canonically conjugate momentum, so P is equal to del L del Q dot, and that would turn out to be simply L Q dot, and in terms of current I can write it as Li. So maybe you recognize that Li is nothing but the magnetic flux in the circuit, which I can represent it by the symbol. So phi here is magnetic flux. So when I take charge as my generalized coordinate, the generalized momentum or conjugate momentum is minus of the magnetic flux in the circuit gives the conjugate momentum in the problem. So the Hamiltonian now is a function of the generalized coordinate q and the momentum phi, and we know that the Hamiltonian is written like this: q dot p, generalized coordinate, the velocity basically, and p generalized momentum minus the Lagrangian. So p is equal to L q dot. So if you put it here, then you will get L q double dot q dot square minus L is half L q dot square minus q square by 2c. So immediately you will get this equation. You will get q square by 2c plus half L q dot square, right? So this is what you will get, and you can in fact write from here, because Hamiltonian is a function of charge and the moment, this q and this magnetic flux. So better we write it like this: q square by 2c plus phi square by 2l, because q dot square is equal to I and we have phi is equal to Li. So I just utilize it, and so this is our Hamiltonian. Okay, so what about the canonically conjugate variables? Here obviously q and phi are the canonically conjugate variable, but to ensure that, let us see, this canonical equation of motion gives us q dot is equal to del h del p, that is the momentum. And now momentum, let me write once again that this is equal to Li, or actually minus phi. Okay, so in fact better I can write this Hamiltonian as h is equal to q square by 2c plus this p square by 2l. So therefore del h del p is simply going to give me p by l, and p by l is nothing but q double dot, right? Because p is equal to lq. That's what I have written here. Yeah, lq dot. So therefore, yeah, so that's correct. And the other one, this momentum p dot is equal to minus del h del q, and this is going to give me from this Hamiltonian I will get minus q by c, and because p dot is equal to lq, so it is lq double dot is equal to minus q by minus q by c. So we get the equation of motion. So quite clearly we are obtaining the equation of motion and correct equation of motion. So q and phi are charge q, and this magnetic flux phi are canonically conjugate variables in the problem, conjugate variables. So therefore we can invoke quantization. Now what we have to do, we just have to replace this q by operator q and phi by operator phi, and that would be equal to is cross, and this Hamiltonian we'll write it as here we have written. So that would be q square by 2c plus phi square by 2l. So this is the way we can quantize LC oscillator. You may actually know that in the Hamiltonian formalism, both generalized coordinate and momentum are given equal weightage. In fact, the Hamiltonian formalism is quite flexible, so we can quantize the LC oscillator taking magnetic flux as our generalized coordinate rather than the charge. So if we take phi as our generalized coordinate, okay, and q as our generalized momentum, so that's, if we do that, only thing is that we have to be careful about the commutation relation here. But anyway, if I take, because if I take phi not minus phi, then that's correct. The commutation relation would remain intact. So I encourage you to do this, and you will indeed get the same expression as your Hamiltonian. That would be phi square by 2L plus q square divided by 2c. That would be the Hamiltonian. Only difference here is that this time the magnetic flux phi, this is magnetic flux phi is now our generalized coordinate, and charge is our new generalized momentum. In fact, let us check whether indeed this is the correct one. So if I put it in the Hamilton's canonical equation of motion, so phi is my generalized coordinate, so therefore phi dot is equal to del h del p tilde, let me write, for our new generalized momentum, which is nothing but the charge. So therefore you will get it to be simply q by c here, because remember here generalized momentum is nothing but charge q. Okay, and phi is magnetic flux, so therefore it is li dot. Okay, that is q by c, and this is correct because this we already know. Okay, this is another thing is about the momentum. P dot is equal to minus del h, the generalized coordinate is phi, and that would be from here we'll get it as phi by L, and this is nothing but minus I, and because P is this generalized momentum, actually P tilde, that is your Q, so Q dot is equal to minus I. This is also, we know that this is correct. Now by the way, in this case the Lagrangian would be turned out to be C by 2 phi dot square minus phi by twice L. Okay, when I take magnetic flux as my generalized coordinate, this is the Lagrangian that I should take. And in fact we'll see that while quantizing transmission line, we should take magnetic flux as our generalized coordinate, not charge q, and we'll discuss about it. Now going back to our transmission line, let us propose qn, charge, as our coordinate and see what happens. As you know, the Lagrangian for the basic unit cell for this transmission line, which is the LC circuit, the Lagrangian is written like this: L is equal to half, here this L represents the inductance, half Li square minus half Q square by C. In fact, this first term is actually called magnetic energy. This is the magnetic energy term, and the second term is the electrical energy, or it's also called the charging energy term. Charging energy. So we need to write down the charging energy and the magnetic energy for the full transmission line. Now given the charge distribution Q, we have to find the current I to write down the Lagrangian for the transmission line. Now we know that from the charge conservation, that rate of change of charge at the node n, Qn dot, is equal to the current that is flowing into the node and the current flowing out of the node. So this we know from charge conservation. We can use this expression to find out the current at node n. So I can write In is equal to Q1 dot plus In plus 1. Now I can express In plus 1 as, again, you can see from this expression itself, I can write it as Qn plus 1 dot here plus In plus 2, and then I can again write it as qn dot plus qn dot n plus 1, q dot n plus 1 plus q dot n plus 2, and in fact I will get another term in plus 2, so we'll get q dot n plus 3 plus, so we'll get a series like this. So as you can see, from this we can try to find out the current, but the problem here is that we cannot write down the magnetic energy term because of this expression here. From the current expression, as you can see, that this is actually results in an infinite sum, and that means that we are running into a problem. If we choose charge as our coordinate, we will not be able to write down the energy term in the Lagrangian or the Hamiltonian. And mind it, you have to note that we have to find magnetic energy at each node, at this node n, then we have to find it at this node as well, n plus 1th node and n minus 1th node, and so on. And already we are running into trouble even with a single node only. So therefore choosing charge as the coordinate is not a good idea while we try to write down the Lagrangian for the transmission line. Now then the next option is what about the magnetic flux? So now let us take magnetic flux, which is our magnetic flux as our coordinate, So we know that the magnetic flux is at a particular node n is a time integral over voltage. So phi n, I can write it as say minus infinity to some time t, and that is the voltage at the node n, and this is the integral. This gives us the magnetic flux, and we know that the voltage at node n, I can write it as q charge at the node n divided by the capacitance dt dash. So from here you can see that I can write charge at the node n as simply capacitance into time rate of change of the flux, magnetic flux. So given the flux phi n at node n, we know the charge qn at node n, and we need to take simply the time derivative of the flux, then we will be able to know the charge. Now what about the current? Because that is where we run into trouble when we took charge as our coordinate. Now let us consider fluxes at node n here, at this node, as well as say n minus 1th node, and take their difference and then take the time derivative. So what I mean to say is this: take the flux at the node n minus 1 and take the flux at node n, and then take the time derivative here. So if I do that from this expression, you can see that I can write it as q n minus 1 minus qn by c. It is easy to, you can easily see this. And what is this quantity? This quantity is nothing but the voltage drop across between these two nodes, and this voltage drop is responsible for the current in, and this I can write as LIN dot. Okay, so we have an equation connecting the time derivative of the magnetic flux to the time derivative of current. So if we integrate it, then we will get phi n minus 1 minus phi n is equal to LIN plus some integration constant, right? This integration constant can be taken to be 0, as in the infinite past say there was nothing, current and fluxes were 0, so therefore I can take this constant to be 0, and then we will simply have phi n minus 1, that is the difference of magnetic fluxes at the nodes, is equal to L into In. In fact, this is the fluxes at nodes, and this is simply the magnetic flux in the coil or in the branch. Okay, magnetic flux in this branch. Okay, so what we get is that we can obtain the current just by taking the differences of magnetic flux, while we can get charge by taking the time derivative of the flux. Now we can write down the Lagrangian for the full transmission line. So the Lagrangian is, because now I have taken the magnetic flux as my coordinate, so the first term would be here now the electrical energy. Just remember that why I take charge as my coordinate, I got the magnetic energy as the first term and the electrical energy as the second term. Now here it would be the reverse, so it would be electrical energy minus the magnetic energy when I take magnetic flux as my coordinate, and that would be, I have to sum up all this I have to find this energy difference at all nodes. So at a particular node n, I have this C by 2 electrical energy, C by 2 phi n dot square, right? That is basically the current. Okay, charge actually, that is the, this is the charge term. Okay, and then I have minus half L In square, that's the current, that's the magnetic energy part, and this I can write as C by 2 phi n dot square minus, now I can express this current in terms of the magnetic flux as phi n minus 1 minus phi n whole square divided by 2L. Here this curly L is the Lagrangian and this L is our inductance. So this is the Lagrangian for the discrete version of the transmission line. Okay, this is the Lagrangian for the discrete version of the transmission line, but it is straightforward to get the continuum version of the transmission line. What we just have to take here, if we go to the continuum, this difference in fluxes, I can express it, should be actually converted to a spatial derivative. A spatial derivative, we can write it as, when we go to the continuum domain, this kind of things we discussed already, that would be say del phi del x, and this sum I have to convert it to an integral. In fact, if you look at observe the transmission line carefully, spacing between the nodes is A, right? That is the unit cell size, and we have to take sum over different nodes, and this I can write it as integral dx. Okay, so then this Lagrangian, this for the discrete transmission line, I can write in this form also. I will explain it. A into small c is the capacitance per unit length. Just recall that capital small c is capacitance per unit length, and then we have a small l, that would be inductance per unit length. That's what we are going to utilize here. So this is small c here. Okay, small c phi dot square minus A by twice L del phi del x whole square, and because as in the limit when A tends to 0, I can write for the continuum case, for the continuum version of the transmission line, I can replace this sum by integral, and I can write dx and the bracketed term would be c by 2 phi dot square minus 1 by 2 small l is the inductance per unit length del phi del x whole square. So this is the Lagrangian for the continuum model, but for our quantization purpose, we will take the discrete model rather than the continuum. So we will consider this Lagrangian, not this continuum one, and along with some boundary conditions. Now the conjugate momentum is, from this Lagrangian we can write it as Pn, the momentum, del L of phi n dot. Phi n, that's the magnetic flux, is our coordinate, so from it we can see that would be simply C into phi n dot, and which is nothing but the charge Qn. And the Hamiltonian for the discrete transmission line would be, that would be Pn momentum into coordinate time derivative the coordinate and minus the Lagrangian, and you can easily work it out, and if you work it out you will find that this would be simply Pn square by 2c plus phi n minus 1 minus phi n square divided by twice L. So as we have already discussed about the quantization of LC circuit earlier, taking the magnetic flux as our coordinate and the charge as our momentum, we found that these are canonically conjugate variables. So therefore here also that's what we will find in the case of transmission line as well. So now we are ready for quantization. So while we quantize it, we now simply replace this coordinate phi n by the corresponding operator, and the momentum Pn, we replace it by the momentum operator, and then write down the Heisenberg uncertainty relation in this commutation form, phi n dot cap Pn, and that is equal to Is cross. Actually, more generally we can write it as we can write phi n and Pn dash is equal to Is cross delta and n dash. In fact, the coordinate and the momentum belonging to different nodes, say phi n, the commutation relation between phi n and the momentum Pn, if this n and n dash are not equal, that means they belong to different nodes, then this commutation relation would be equal to 0. So as you can see, now we have this quantum mechanical Hamiltonian that we have to write in this operator form, that would be equal to Pn square by 2c plus phi n minus 1 minus phi n cap whole square by 2l. Okay, this is quadratic in position and quadratic in momentum, and it should remind you about the so-called harmonic oscillator, simple harmonic oscillator Hamiltonian. Also, you should note that this Hamiltonian is actually translationally invariant, because the transmission line that we have taken, this transmission line is translationally invariant. Each cell in the transmission line is equivalent to one another, and in fact this is what we are going to exploit. That means the invariance, translational invariance of the transmission line, we are going to exploit to write the Hamiltonian in terms of normal coordinates by choosing appropriate normal modes, and we are going to discuss it in the next class. So in this class we learned about transmission line, and we saw that indeed a transmission line supports a wave in the form of a current. And then we also learned how to quantize an LC oscillator, which is the building block of a transmission line. And it turns out that taking the magnetic flux as the coordinate rather than the charge is more beneficial if we are interested in quantizing a transmission line. In fact, taking the Hamiltonian for the discrete transmission line, we saw how it can be quantized. However, this Hamiltonian can be written in a more useful form using so-called normal coordinates, and that's what we are going to do in the next class. So see you in the next class. Thank you.